In this video, we're going to find the limit of this multivariable function. So this is your x-axis, this is your y-axis. So your x-axis, so the origin is here, your x-axis is here, your y-axis is here. So along x equals 0, which is along this plane here, along this plane, put 0 into here, this whole thing here would become e to the power 0. Well, if you put 0 into here, this whole thing here will then become 0 over y, and then limit as y tends to 0. So this thing here equals 0 along that plane. So we suspect our limit is 0. We suspect our limit is 0. In this case here, it's pointless considering along y equals 0, because if you look at y, this is your y-axis here. The origin's here, so your y-axis, y equals 0 is along this plane here. But then when y equals 0, it breaks down. So we can't really approach it along this axis here because it's undefined. So it's pointless considering along y equals 0. So let's just use this only, and we suspect our limit is 0. We suspect it's 0. So if the limit truly exists, then this thing, take away our suspected limit of 0, should, and then you take the absolute value, it should equal 0. Normally we would try and use the squeeze theorem and trap this in between two things. But in this scenario here, in this instance, we can evaluate this thing directly without having to trap it in between two things. So let's try and evaluate this. So we are really trying to show that this thing here equals 0. Well, this thing take away 0 is the same as this thing. So let's try and show that this equals 0 as x and y heads towards 0. So at the moment if y equals 0, then the whole thing breaks down. When it comes to evaluating limits of multivariable functions, try to keep an eye out for Young's inequality. Try to keep an eye out for this thing here, and now you've got to try and keep an eye out for this thing here. Remember, from single variable calculus, this is y equals, well, this is single variable calculus. Remember this thing here, to work out the derivative of this thing, evaluated, so wait there, dy by dx equals e to the power of x. So here we are really evaluating it at x equals 0. So to evaluate this, we would set up 2 points. This is 0 here. The height here is given by e to the power of h, and then take away the height here, which is 1. Take away 1. So this thing here will give us this height here, divided by h. Take the limit as h tends to 0, and it should be 1 because the gradient here, dy by dx equals e to the power of x, evaluate it as 0, so that would be e to the power of 0. Well, you should recognize this by now. Okay, so when it comes to evaluating limits of multivariable functions, keep an eye out for this, keep an eye out for this, and now keep an eye out for this. But the thing is, this thing is not the same as this thing here. So we need to multiply top and bottom by x. We need to multiply top and bottom by x. That will then give us this thing here. Oh, by the way, I need to go back one step. Back to here. Here I'm taking the limit on the limit is on the inside of the absolute value here. Here the limit is on the outside of the absolute value. It makes no difference, because if you consider this, let's say you've got a function here, and then you've got the exact same function but with the absolute value here, so something like this. So here you're taking the limit of this function here, so you're approaching here, and then you're approaching here, and once you've got the limit, when you type, let's just imagine the limit is -7, and now take the absolute value here, that would be +7. Well, down here you're taking the limit of the imaginary function here, so here you're approaching 0 here. So it would be the same thing. It would take you to 7. The point here is that it makes no difference. You can actually drag this limit out here and just evaluate this. It makes no difference. Well, anyway, back to this thing here. So here you're trying to get these two to be the same. So you would times top and bottom by the same thing, x. Times top and bottom by x. That will then give you this thing here. And notice that this thing and this thing are exactly the same. That's like this thing is exactly the same as this thing, and x and y heading towards the origin is the same as h heading towards the origin, and they're on par with each other. So so we know that this thing here should equal 1 as you approach the origin, should equal 1. Well, anyway, from here that will then take us to here. We know that this thing is 1 when x and y heads towards the origin. So now it boils down to this. Now you can see that nothing here really breaks down. Nothing breaks down. Absolute value of x as x and y heads towards origin. So it does equal 0. So the whole limit equals 0. Okay.